Hi students, welcome to the course Probability and Statistics. Let's look at the typical problem involving probability. See, there is a communication system consisting of 50 seemingly identical antennas that are lined up, and the resulting system will be able to receive signal as long as there are no two consecutive defective antennas. Such a system is called functional. So the system will be functional as long as no two consecutive antennas are defective. If it turns out that 20 of them are defective. In general, say we have n antennas are lined up, out of which m are defective. The question of interest is, what is the probability the resulting system will be functional? Okay, now let's look at a simple case here. N equal to 4, m equal to 2. That means we have 4 antennas are lined up in which 2 are defective. Let's denote defective antenna by 0, non-defective antenna by 1. Then we see there are 6 possible configurations. As you can see, first 3 configurations do not have a consecutive zeros, so they will give functional systems. Last 3 do have a consecutive zeros, so they will give non-functional systems. So it is reasonable to take 3 by 6, which is 1 by 2, as desired probability. Fine. Now what about general case? For general m and n. In particular for our problem, m equal to 20 and n equal to 50. Of course, you may feel like doing the same thing, that list out all possible configurations, but let me tell you, you will die by aging before you're done listing all, because there are a huge number of possible configurations that you will realize later. So it's not feasible to list out all possible configurations to count the total and the number of configurations that result in functional systems. But that doesn't mean that we should give up on problems like this. Okay, all we need is some effective counting techniques. Okay, many problems in probability can be solved simply by counting number of ways certain things can occur. Okay, the mathematical theory of counting is called combinatorics. Combinatorics is concerned with arrangement of objects of some set into certain patterns satisfying a specific rules. Okay. Now there are two types of problems that occur in practice. The first one is existence question. Whether arrangements we are interested in possible or not. That is the existence problem. Next, enumeration. Once answer is yes, you want to count how many possible arrangements are there. Let me give an example of a existence problem. A chess master who has 11 weeks to prepare for the tournament decides to play at least one game every day, but in order not to tire himself, he decides not to play more than 12 games during any calendar week, so that there exist consecutive days during which the chess master will have played exactly 21 games. How can we prove something like this? Okay, so to tackle problems like this and wide variety of interesting problems with surprising results, we use something called pigeonhole principle. It roughly says that if a lot of pigeons fly into not too many holes, then at least one pigeonhole will have 2 or more pigeons. Let me put it formally. If n plus 1 or more pigeons fly into n pigeonholes, then at least one pigeonhole has 2 or more of pigeons. Simple application. Among 13 people, there are at least 2 who celebrate their birthday in the same month. Here, 13 people, you think like a 13 pigeons, and the 12 months, think like a 12 pigeonholes. According to above principle, at least 2 people should be celebrating birthday in the same month. Now let's get back to chess master problem. Here, chess master has 11 weeks to prepare for the tournament, and each day he wants to play at least one game, but not more than 12 games in a week. We have to show that there exist consecutive days during which the chess master will have played exactly 21 games. Okay. Let A denote the number of games played in up to ith day. for I equal to 1 to 77 days. 76, 11 weeks, right? 11 into 7. Okay. A1 represent number of games played in the first day. A2 represent number of games played in the first 2 days. A3 represent number of games played in the first 3 days, and so on. Okay. So immediately we can observe that A1 strictly less than A2, strictly less than A3, and so on, strictly less than A77, because each day the chess master plays at least one game, so the count strictly increasing. Also, 1 less than or equal to A1 because the first day he must have played at least one game. Also, A77 less than or equal to 132 because 77, 11 weeks, right? In each week, he can play at most 12 games. So 11 into 12, 132, right? Fine. Now, if I add 21 to each side, then I'll end up with a new sequence A1 plus 21, strictly less than A2 plus 21, and so on. Okay. A1 here A77 plus 21 less than or equal to 132 plus 21, which is 153. So now we created 77 plus 77, total 154 numbers. Okay, two lists. In above list we have a 77 numbers, below list also we have a 77 numbers, total 154, but they all lies between 1 and 153. Okay, so each of these 154 numbers, A1 to A77 and A1 plus 21 to A77 plus 21, lies between 1 and 153. But they are 154 numbers. So by pigeonhole principle, at least two must be same. But those two cannot come from the same list. Here in above list, none of the two can be same. Same thing with the below. So those two numbers, one must be coming from above list and other must be coming from below list. Okay. So therefore we must have AI equal to AJ plus 21 for some j less than I. That means what? On the days j plus 1, j plus 2, so on, I. During this period, j plus 1 to ith day, the chess master must have played 21 games because AI minus AJ represent what? Which is 21. Which represent number of games played during the days j plus 1 to I. Okay. Next, generalized pigeonhole principle, which says that if nk plus 1 or more pigeons fly into n pigeonholes, then at least one pigeonhole has k plus 1 or more pigeons. Okay. Simple application is among 100 people, there are at least 9 who celebrate their birthday in the same month. Because 100 we can realize as 12 into 8 plus 4, which is more than 12 into 8 plus 1. By generalized pigeonhole principle, there must be 8 plus 1 or more people celebrating their birthday in the same month. Okay. Next, example of enumeration problem. Each user on a computer system has a password which is 6 to 8 characters long, where each character is lowercase letter or a digit, and each password must contain at least one digit. How many possible passwords are there? Okay, so how to answer questions like this? Okay, to tackle problems like this, we are going to develop some counting principles. Okay, so we'll come back to this. Let's go and look at some basic principle called product rule, or you can say multiplication principle. Product rule or multiplication principle. Before I put it formally, let me motivate you with an example. Say you went to fashion store to buy a dress for yourself, and there are only 3 t-shirts and 4 jeans of your size, and you happen to like them all. Question is, how many ways can you select your dress? Here first, there are 3 ways you can pick your t-shirt. For each way of picking t-shirt, there are 4 ways you can pick jeans. See, there are 12 dresses you can get, right? Let me put it this way. The procedure of selecting the dress can be broken down into sequence of 2 tasks. Task 1 is selecting t-shirt. Task 2 is selecting jeans. Here, task 1 can be done 3 ways as there are 3 t-shirts. For each way of doing task 1, there are 4 ways to do task 2 because there are 4 jeans. So there are 12, 3 into 4 choices for your dress. This is what product rule says. Okay, let me put it formally. Suppose a procedure can be broken down into sequence of 2 tasks. If a task 1 can be done in m ways, and each way of doing task 1, if there are n ways to do task 2, then the procedure can be done m into n ways. Okay, let me state generalized version. Suppose a procedure can be broken down into sequence of k tasks if there are ni ways to do task I, regardless of how previous tasks were done for I equal to 1 to k, then procedure can be done n1 into n2 into so on nk ways. This is generalized version of product rule. How many 4-digit pins are possible to set for your debit card? Okay, debit card pin look like this. It's a string of digits with a length 4, right? It will be in the form P1, P2, P3, P4. Let's think this way. The procedure of making debit card pin can be broken down into sequence of 4 tasks. Task 1 is deciding what P1 is. Task 2 is deciding what P2 is. Task 3 is deciding what P3 is. Task 4 is deciding what P4 is. Okay. So here each task can be done 10 ways. So by product rule, this procedure can be done 10 into 10 into 10 into 10, 10 to the power of 4 ways. Okay. Here task I is choosing Pi for I equal to 1 to 4, and each task can be done 10 ways. So therefore, by product rule, this procedure can be done 10 into 10 into 10, 10 to the power of 4 ways. So therefore, there are 10 to the power of 4 pins are possible for your debit card. Okay. Next, show that the number of binary strings of length n is 2 to the power of n. So I hope you know binary string is a string of bits 0s and 1. So it will be in this form b1, b2, so on bn, where each bi either 0 or 1 for I equal to 1 to so on n. Okay. Again, if you think like the procedure of making binary string can be broken down into sequence of n tasks. Task I is choosing bi. Each task can be done 2 ways. So by product rule, this procedure can be done 2 into 2 into 2 n times. So which is 2 to the power of n. So there are 2 to the power of n binary strings of length n are there. Okay, keep in mind. Note, if A comma B are finite sets, then number of elements in A cross B equal to number of elements in A into number of elements in B. This is nothing but product rule because here A cross B is Cartesian product of A comma B, which consisting of order pairs A comma B, where A coming from A, B coming from B. If you think like A consisting of t-shirts, B consisting of jeans, then A cross B will be consisting of your dresses. Okay, so this perfectly makes sense. So number of elements in A cross B going to be number of elements in A into number of elements in B. If we generalize this, if A1, A2, A so on, AK are finite sets, then number of elements in the product A1 cross A2 cross AK, here this is set consisting of the k tuple A1, A2 so on, AK, where AI coming from corresponding capital AI for I equal to 1 to so on K. Okay. The size of this set simply going to be product of corresponding sizes A1 number of elements in A1 into number of elements in A2 into so on number of elements in AK. Fine. Next, sum rule or addition principle. Again, before I put it formally, let me motivate you with an example. Say a JEE aspirant who cleared IIT-JEE trying to get into IIT Kanpur, where he can get into either science stream or engineering stream. See, there are 8 branches in the engineering, 5 branches in the science. So question of interest is how many choices does he have to pick his branch? Answer is 13 with common sense 5 plus 8. Let me put it this way. The task of picking branch in IIT Kanpur can be done in one of the 5 science ways or one of the 8 engineering ways. So this task can be done in 5 plus 8 ways. Here, none of the science branch same as any of the engineering branch. Okay. So now let me put it formally. Sum rule. Suppose a task can be done either in one of m ways or in one of n ways, and none of m ways same as any of n ways, then the task can be done m plus n ways. This is what sum rule says. Generalized version, suppose a task can be done in one of n1 ways or in one of n2 ways or so on in one of nk ways, where none of ni ways same as any of nj ways, then the task can be done n1 plus n2 plus so on nk ways. This is generalized version of sum rule. Simple problem. A person wants to travel from city A to city B. There are 10 buses, 5 trains and 3 flights to travel from city A to city B. Then how many ways can he go from city A to city B? Simple. Answer is 18 because the task of traveling from city A to city B can be done in one of the 10 bus ways or in one of the 5 train ways or in one of the 3 flight ways. So by some rule, this task can be done 10 plus 5 plus 3 ways. Okay, so answer is 18. Note, if A and B are finite sets and A intersection B empty, that means there is no overlapping, the number of elements in A and B equal to number of elements in A plus number of elements in B. This is nothing but sum rule. Okay, the task of picking an element in A and B can be done in one of the number of elements in A ways or one of the number of elements in B ways. By sum rule, the number of elements in A and B should be number of elements in A plus number of elements in B, provided there is no overlapping between these sets A and B. Generalization, A1, A2, so on, AK, finite sets, and AI intersection AJ equal to empty for I not equal J. None of the two overlapping here. Then number of elements in A1 union A2 union so on AK is going to be number of elements in A1 plus number of elements in A2 plus so on number of elements in AK. This is nothing but generalized sum rule. Now, subtraction principle. Okay, look at this grid. If I ask you how many white cells are there in the grid. What I do, since I am too lazy, I'll count the black ones. 1, 2, 3, 4, 5, 6, 7. There are 7 black cells. Total cells are also easy for me to count because I can see 8 by 8 grid. So 8 into 8, 64. Easily I can get 64 total count, total cells. So 64 minus 7, 57. This is the count for number of white cells. See here, the counting black cells is easy. Also counting total cells also easy. Then counting white cells. In this situation, we use this technique. This is something called subtraction principle. What it says, if S be a universal set, if A is a subset of S, the number of elements in A equal to number of elements in S minus number of elements in A complement. This is a known fact, but when to use it? Because sometimes the stuff you don't like may be easy to count and also to get the count for total stuff. In that case, you can use these principles to get the count for stuff you like. Okay. Example, how many pins are possible for your debit card with at least 17? Maybe your lucky number. Okay, if you think for 1 minute, if you directly apply product rule or sum rule, it will be very difficult because there are too many cases to deal with. Because when I say at least 17, maybe 17 or 27 or 37 or 47. There are a lot of cases. There will be a lot of overlapping. Okay, so that's why we think this way. Let us be the all possible pins for your debit card. It's easy to count. I think we already counted. It is 10 to the power of 4. Let A be the set of all pins we like. Okay, with 7. Then A complement will be the set of all pins we don't like without 7. Now, here getting count for A complement will be easy. See, number of elements in S, like I said, is 10 to the power of 4. And number of elements in A complement will be going to be 9 to the power of 4. Because simply don't use 7. Each task can be done 9 ways because you are not using 7 anymore. So 9 into 9 into 9, 4 times 9 to the power of 4. So by subtraction principle, number of elements in A are going to be number of elements in S minus number of elements in A complement, which is 10 to the power of minus 9 to the power of 4, which is 3439. So this many pins are possible with at least 17. Okay, this is how you have to apply this subtraction principle. Now let's get back to the enumeration problem we posed. Each user on the computer system has a password which is 6 to 8 character long, where each character is lowercase letter or digit, and each password must contain at least 1 digit. How many possible passwords are there? Now we are in a position to answer this one because we have all the tools that are needed to solve this problem. Okay, now we are going to use the 3 principles: product rule, sum rule, and subtraction principle to get the count for this problem. Here the password alphabet is the lowercase alphabet A to Z and digits 0 to 9. Okay, now let P denote the set of all possible passwords with the required condition. Now let Pi denote the set of all passwords for the computer with a required condition of length I. So that means all passwords I am classifying into 3 types: length 6, length 7, length 8. So that's why the P must be equal to P6 union, P7 union, P8. Okay. So what is P6? All passwords of length 6 with a required condition. P7 is all passwords of length 7 with a required condition. Similarly, P8. Now, and they are pairwise disjoint. So by sum rule, the number of elements in P should be number of elements in P6 plus number of elements in P7 plus number of elements in P8. Sum rule. Okay. Now let's get the count for each of the P6, P7, P8. Now number of elements in Pi going to be, by subtraction principle, 36 to the power of I minus 26 to the power of I with at least one digit. Total passwords are possible of length I is 36 to the power of I minus the passwords we don't like without digit. They are 26 to the power of I. So by subtraction principle, answer is 36 to the power of I minus 26 to the power of I. Here we also use product rule because 36 into 36 into 36 I times, right? Yeah, here combination of product rule and subtraction principle. Now let's put them back in sum rule. Number of elements in P going to be number of passwords of length 6 of required condition, length 7 of required condition plus length 8. This gets simplified to this number. Okay, so finally we solve the problem that we posed, enumeration example problem. Okay, let's count all the subsets of set E1, E2, E3. Let me list them. I can. There are 8 subset: empty set, singleton E1, singleton E2, singleton E3, set E1, E2, set E2, E3, set E1, E3, and the whole set E1, E2, E3. If I have a close look at these subsets, I can see a pattern. They almost look like a binary string of length 3 for me because this is my encoding. Each subset of E1, E2, E3 I am mapping to binary string of length 3 B1, B2, B3. In the B1, B2, B3, the BI equal to 1 if and only if the corresponding EI in the subset. Okay, so that means the empty set get mapped to 0, 0, 0 because E1 is not there, E2 is not there, E3 is not there. So in corresponding places I put 0, 0, 0. Singleton E1 map to 1, 0, 0 because E1 is there, no E2, no E3. Similarly, E2 encoding is this, E3 encoding is this, E1, E2, 1, 1, 0, E2, E3, 0, 1, 1, E1, E3, 1, 0, 1. See, so there is a one-to-one correspondence between these subsets and this binary string of length 3. So there is a bijection between subsets of set E1, E2, E3 to binary string of length 3. So counting subsets of E1, E2, E3 is same as counting binary string of length 3. And we already know effective method of counting binary string of length n. We said it is 2 to the power of n. Okay, let us generalize this. We have a set E, E1, E2, En. My claim is that number of subsets of E is going to be 2 to the power of n. Same idea. So we are going to, let me say, A is power set of E. That means A consists of all subsets of E. Now let me take B, which is a binary string of length n. B, see the element of B look like B1, B2, Bn, where Bi is either 0 or 1. So we already know the number of elements in B is going to be 2 to the power of n. Number of binary string of length n is 2 to the power of n. So we know count for B. Now we are going to produce bijection between A and B. A is what? Power set of E, means it consists of all subsets of E. So this is my mapping. So X in A, X is a subset of E, map to X1, X2, Xn, which is a binary string. Here Xi will be 1 if and only if corresponding EI in the subset. Same idea. So one can easily check it is a bijection mapping. So that is possible only when the number of elements in domain same as number of elements in codomain. But we already know number of elements in B 2 to the power of n. That's why number of elements in power set of E is going to be 2 to the power of n. Okay, so this is something called pattern recognition. It's a very we pretty much use all the time. Okay, pattern recognition. It says suppose A is a set for which we wish to get count, and if we can produce a bijection between A to some other set B whose count we already know, then number of elements in A must be equal to number of elements in B. Okay. Theorem. If let A and B are two sets with number of elements in A equal to R, number of elements in B equal to N, the number of function from A to B is N to the power of R. You should know what is a function, then you can make them, right? Then you will know the procedure of making function. Let's say A is a set with the R elements A1, A2, so on, AR. B is a set with the N elements, say B1, B2, so on, Bn. Okay. Function means every element in A should have a unique image in B. Let's try to make them. Let's try to break down the procedure of making function. The procedure of making function from A to B can be broken down to sequence of R tasks. Here, task 1 is mapping A1 to some element of B. Task 2 is mapping A2 to some element of B. So on, tasks are going to be mapping AR to some element of B. So task I is what? Mapping AI to some element of B. No restriction. So for I equal to 1, 2, so on R. So here each task can be done n ways. Number of elements in B ways can be done n ways. So by product rule, this procedure can be done n into n, so on n r times, which is n to the power of r. So that's why the number of functions from A to B going to be n to the power of r. Next, A and B are two sets where number of elements in A equal to R, number of elements in B is N, where R less than or equal to N. Then only one function possible. The number of one function from A to B is this, N into N minus 1 into N minus 2 into so on, N minus R plus 1. Again, same idea. The procedure of making one function from A to B. What is the one function? The function where different elements should have a different images. Okay. So, for example, task I is what? Task 1, task I is mapping A to some element of B which is not used by previous tasks. Okay, so that means task 1 can be done n ways, but task 2 can be done only n minus 1 ways because we can't use image of A1 for A2. Task 3 can be done n minus 2 ways because we cannot use images of A1, A2 for A3. So on, task R can be done n minus of R minus 1 because we can't use the images of A1, A2, AR minus 1 for AR to map. So that's why, so by product rule, the answer going to be n into n minus 1 into n minus 2 into, so on n minus, if you multiply n minus R plus 1. Okay. So when A has R elements, B has N elements, the number of 1 function from A to B is this, n into n minus 1 into n minus 2 into so on, n minus r plus 1. Next, corollary. If A and B are two sets where number of elements in A equal to number of elements in B which equal to n, the number of bijective function from A to B is n factorial. Hope you know n factorial means n into n minus 1 into up to 2 into 1. Okay, you should know one fact that the bijection possible only when A and B having same number of elements. In that case, a function is bijection if and only if it is 1, 1. Okay, so it's enough to count 1, 1 functions here. So what is a 1, 1 function? Here r equal to also n, right? So the number of 1, 1 functions will be same as in this case number of bijections. If you simply put r equal to n in the previous formula, n into n minus 1, n minus 2, up to we go n minus r plus 1, but r equal to n here, this one, so n cancel. Now n into n minus 1 into n minus 2 into so on 3 into 2 into 1, which is exactly n factorial. Okay, look at the example 1. How many ways can we distribute 4 chocolates to 6 children? Here I have to assume that chocolates of different brand, otherwise it would be different. Anyway, children's anyway different, so I don't have to mention that 6 different children. Fine. So here the technical conditions are you can't share chocolate to 2 child or something. 1 chocolate should go to unique child. 1 child can get any number of chocolates. So no restriction. As long as you don't keep any chocolates and you distribute everything. Also you don't share a single chocolate to 2 people like that. Fine. 1 chocolate should go to 1 child. Fine. Now in that case, each distribution look like function from set with a 4 chocolates to set with a 6 children. Okay, we know already how to count function from set with r elements to set with m elements. So answer will be because of pattern recognition. These distribution I recognize as functions. Okay, so answer I'm writing directly 6 to the power of 4. So this many ways you can distribute 4 chocolates to 6 children with no restriction. Next question. How many ways can we distribute 4 chocolates to 6 children so that each children can get at most 1. At most 1 means 0 or 1. This is also function, but 2 chocolate cannot go to the same child. Means what? It is a 1, 1 function. So because of pattern recognition, there is a bijection between this kind of distribution to 1, 1 function from set with a 4 elements to set with a 6 elements. That's why answer going to be what? 6 into 6 minus 1 into 6 minus 2 into 6 minus 3 till 4 minus 1, right? 4 plus 1, so 6 minus 3. So this is going to be the answer. Whatever it is, 6 into 5 into 4 into 3. Okay. 30 into 12. 360. Okay. 360 ways you can distribute with this condition. Okay. Fine. Next. Example 3. In a classroom, there are 30 seats that are occupied by 30 students. A teacher wants to shuffle the students as he decided to conduct a quiz. How many seating arrangements are possible? Here, each seating arrangement can be seen as bijection between students to seats. Okay, so here each seating arrangement can be recognized as bijection from students to seats. Okay, so that's why there is a one-to-one correspondence between these bijections and the seating arrangement. So by pattern recognition, the answer should be same as number of bijection from set with a 30 elements to set with a 30 elements. Okay, so think like A is a set of students, B is a set of seats. So how many bijections are possible? Number of bijections are 30 factorial. Okay, so that would be the answer. Okay, permutations and combination. From given set of objects, if we make an ordered selection of some objects where we give an importance to order, then it is a permutation. If you make an ordered selection, like picking a group where we don't care about an order of the selection, in that case, that selection is called combination. For example, let's say there are 5 people and they got a fancy camera, and so they are taking picture 3 at a time because one is operating camera, one is holding the light. So at a time 3 can take a picture. If they stand in a line for a picture, then order matters. Then it is going to be permutation problem. If they gathered in a group for a picture, then it is going to be a combination problem because we don't care about an order. When they gathered in a group, there is no meaning of first person, second person, or left to right to. There is no meaning. Okay, fine. Let me define. First, we talk about permutations. Permutation. Let R and N are non-negative integers. R permutation of n objects is the ordered selection of R of n objects. That means there are n objects. If we make an ordered selection means we are giving importance to order of the selection. Then that selection is going to be R permutation of n objects. Okay. If we use all objects in a permutation, then we simply call permutation of n objects. It's terminology. For example, let us say we have 3 objects A, B, C. Okay. So now how many one permutation we can make? 3. A is the one permutation, B is the one permutation, C is the one permutation. What about 2 permutations? A, B, A, C, B, A, B, C, C, A, C, B. What about 3 permutations? A, B, C, C, A, B, B, A, C, B, C, A, C, B, C, B, A. We can't make any 4 permutations that are not possible. Here we don't repeat objects. But keep in mind. We'll consider those cases later. And there is a 1-0 permutation, a permutation with no objects. It's a kind of empty one. Okay, it makes sense. Now let's give a notation. Here NPR denotes number of R permutations of n objects. Okay, if you're introducing a notation, NPR always going to mean number of R permutations that are possible out of n objects. Now, so from our experience, we can see that 3p0 is 1, there is a 1 empty permutation, 3p1 is 3, there are 3 1 permutations of 3 objects, 3p2 we got 6, 3p3 also we got 6, and 3p4 is 0, of course 3p5 also will be 0. Now, what about NPR? So can we get a nice formula so that every time we don't have to list out like we did earlier. Okay, theorem. If 0 less than or equal to r less than or equal to n, then NPR equal to n factorial by n minus r factorial. Okay, fine. First, let me consider an example. Let me take a set of 5 objects A, B, C, D, E. Let me look at some 3 permutations of 5 objects. So 3 permutations of S. Let me write some B, D, A. One more thing, C, A, E. Okay. Now each of these 3 permutation I am going to recognize as one function from their position to S. What are the positions here? 1, 2, 3. There are 3 positions. So first one 1, 2, 3 to S, A, B, C, D, E. So 1 map to B because first position is B. Second position go to D. Third position go to A. So I'm going to recognize BDA as a 1 function from their positions 1, 2, 3 to set S. Similarly, this one also I'm going to recognize like this. 1 go to C, 2 go to A, 3 go to E. Like that. Okay. So if you take a S with a set with a n objects, okay, any R permutation of S, why we get a 1 function? Because we don't repeat objects in the permutation. That's why the corresponding function is going to be 1 for sure. Any R permutation of S can be seen as 1 function from their positions 1, 2, 3, so on, or to S. So S has an element. So we know how to count such a 1 function. We know that there are n into n minus 1 into n minus 2 into so on, n minus r plus 1 functions are there. So that many r permutations will be there because of pattern recognition. We see 1-to-1 correspondence between these 1 functions and the r permutation that we are interested. Okay. Now to simplify this, let's multiply and divide by n minus r factorial. So that will make the numerator n factorial, denominator as it is n minus r factorial. So this is NPR, the number of r permutations of an object. Corollary, number of permutations of n objects. Permutations of n object means permutation using all objects at a time. Simply like a n permutations of n objects. That means how many will be there? NPN. According to above formula, NPN. NPN means n factorial by n minus n factorial. The denominator is 0 factorial, so it should be 1. So n factorial. Okay. So there are n factorial permutations of n objects. Next. Look at this example. Suppose there are 8 runners in a race. Winner receives gold medal. Second place finisher receives silver medal. Third place finisher receives bronze medal. How many different ways there to award these medals? Out of 8, any 3 can win, and those 3 also order matters. who is gold medal matters, who is silver matters, who is bronze matters. Okay, that's why it's a ordered selection. So answer will be 8p3. Simple. You have to recognize these things as a 3 permutations of 8 objects. Okay. Example, let there are n students in which no two students are of the same height. Question is, how many ways can we make our students stand them in a line so that they are in ascending order of heights? If I don't put this condition, my answer would have been NPR. We know that it is wrong because we are not following this condition. So can we fix this? Answer is yes, because see, for every selection of R students, there are R factorial permutations are possible, but in which only one is correct, right? Only one permutation will be in the ascending order of heights. That means in NPR, everything overcounted R factorial times. So how to fix this? You just divide like this. You divide NPR by R factorial. This will give you n factorial by n minus r factorial by r factorial, means this is n factorial by n minus r factorial r factorial. So this is going to become simply npr by r factorial. Okay. So sometimes doing mistake, fixing also nice technique. Exercise. Let us see the set with the elements 1, 2, so on n. Script is going to consist of all R tuples I1, I2, IR, where I1 is strictly less than, I2 is strictly less than, so on, IR. Then the number of elements in script S. This is exactly same as the above problem. I hope you can see that. The answer also would be same, NPR by R factorial. Just do it. Next, circular permutation. So far, the permutations we consider something called linear permutation because they are arranged in a line. What if you want to arrange them in a circle? Okay. Look at these 6 animals. They are standing in a circle. So there is no question of first, second, third, so on. Now they are marching in a circle. Now there is no question of south, north, east, like that. Now we already know there are 6 factorial ways we can arrange them on a line. Now they are arranged in a circle. Okay. Now I'm wondering if I can see some connection between number of linear arrangements and circular arrangements. If I cut this circle at any place, it will become a linear permutation, right? But I have 6 choices. I can cut at 6 different places. All will generate 6 different linear permutations. Look at this. See, this single circular permutation is giving 6 different linear permutations. So, if I say 6 factorial, answer would be wrong because in that 6 factorial, single circular permutation counted 6 times. Okay, to fix it, what we do, we divide by 6. So 6 factorial by 6, 5 factorial would be the correct answer. Okay, now theorem. The number of R circular permutation of n objects equal to npr by r. We just realized that connection between number of R circular permutation and number of R linear permutation of n objects, right? So what we realized is R times number of circular R permutations equal to number of R linear permutations. So the right hand side is NPR, we know. That's why number of circular R permutations equal to, if you bring R this side, NPR by R. Okay, that's it. Next, corollary. Number of circular permutation of n objects. If I use n objects at a time, just straightforward, npn by n. Npn means n factorial by n, that will give you n minus 1 factorial. Okay, example, 10 people including 2 who do not wish to sit next to one another are to be seated around round table. How many circular seating arrangements are there? Okay, now let me solve it using subtraction principle. Total seating arrangements, there are 10 people, right? So 10 minus 1 factorial, which is 9 factorial. So from which let us subtract circular arrangements in which those two are actually sitting together, particular people, right? So first let us think about how many ways we can arrange these 10 people so that two particular people always sit together. If you want to make sure that they always sit together, you better tie them. How many ways you can tie them? The task 1, 2 factorial ways. Now you treat those two people as a single person, then remaining 8 people total. Now you feel like you have 9 people. Now try to arrange them in circular fashion so that those two always will be together. So how many ways you can do that? 8 factorial, because 9 minus 1 factorial, right? Okay, so here we are doing two tasks. Task 1, tying. Tying can be done 2 factorial ways. Task 2, arranging 9 people, 8 plus 1 tied people. So which can be done 8 factorial ways. So in this many circular arrangements, those two particular people are always sitting together. So what we do, let us subtract those from the total. Okay, now 9 factorial means 9 into 8 factorial. Here 2 factorial into 8 factorial. If you take 8 factorial common, 9 minus 2. So the answer is 7 into 8 factorial. Example, what is the number of necklaces that can be made from 20 beads each of different color? Here, each necklace can be seen as circular permutation of 20 objects. In this problem, a circular permutation and one obtained by flipping it need to be considered same. Okay, so that's why here answer is not just 20 minus 1 factorial. Actually, we need to do by 2. Okay. Okay, now. Okay, now. Okay, permutations with repetitions allowed. We have seen some examples before. Debit card pins are examples of 4 permutations of 10 objects with repetition allowed. Binary strings of length 3 are examples of 3 permutations of 2 objects with repetition allowed. Okay. Now in general, we can talk about R permutations of n objects with repetition. So theorem, the number of R permutations of n object with repetition is going to be n to the power of R. Straightforward application of product rule. Okay. Now permutations with constant repetitions. Earlier, when I said permutations with repetition allowed, there each object can be repeated any number of times. But here, each object should be repeated a constant number of times. Okay, look at this example. The question, how many words can be formed using the letters of the word pepper? In the pepper, there are 3 P's and 2 E's, 1 R. So every word that we are going to form using the letters of the word pepper should have 3 P's and 2 E's and 1 R. This is what we mean by constant repetitions. Okay, now let's try to count the number of words that can be formed using the letters of the word pepper. See, in pepper, 3 P's are identical, so they colored same red. 2 E's are identical, so they colored same green. And R got its own color blue. Now for a moment, let's pretend that all these 6 letters are different. So let me color them differently. Now see, these 6 letters are colored differently. Now there should be 6 factorial permutations for these 6 differently colored letters. Let me list them all. We should be getting 720, 6 factorial. Now what we do, let's color their original color back. Now you see, first 12 are same, 1 to 12, you see. Next to 13 to 24 also same. Next 24 to 25 to 36 also same. As you see, so now each one got repeated 12 times. Now, so let me separate with different highlights for each block here. So there are 60 differently colored blocks are there. Here, among 6 factorial, everything is got counted 12 times. The 12 is 3 factorial times 2 factorial times 1 factorial. Because if you shuffle P's among P's, E's among E's, R's among R's, then resulting permutation will not change. So this shuffling can be done 3 factorial into 2 factorial into 1 factorial ways. That's why everything got overcounted exactly 3 factorial times 2 factorial times 1 factorial. Okay. So we actually got only 60 different permutations. All this got repeated exactly 12 times. So to fix it, what we do is we divide 6 factorial by 3 factorial times 2 factorial times 1 factorial. Now you can see that. See, in each block, in each colored block, we have a same permutations. Okay? Okay, fine. Therefore, the number of words that can be formed using the letters of the word pepper is 6 factorial by 3 factorial times 2 factorial times 1 factorial. This can be generalized. If there are n objects in which n1 are alike, n2 are alike, so on, nk are alike, where n1 plus n2 plus so on nk equal to n actually, then the number of different permutations of these n objects is n factorial by n1 factorial, n2 factorial, so on nk factorial. Now, this has got a notation actually. This n factorial by n1 factorial, n2 factorial, so on nk factorial actually denoted by this left hand side, that can be read as n choose n1 comma n2 comma so on nk. These are called multinomial coefficients because of their role in multinomial theorem. We will see later. Thank you.